Hello everyone. Thank you for tuning in to our talk in the Experimental Archaeology World Tour online conference. Today we will be presenting some preliminary results from our new experimental research in controlled lavawa flaking. Archaeologists have long used replicative flint knapping to study archaeological stone tools by recreating archaeological forms using materials and techniques thought to be used in the past. This approach allows us to get at the technical skills and intentions of past toolmakers. However, this approach also faces challenges of subjectivity, as interpretations are based heavily on the personal experience of the modern napper. Since the 1970s, a number of researchers have employed mechanical setups to simulate flake formation under controlled settings. This alternative approach aims to understand the flake formation process by isolating the effect of individual knapping factors on flake variability. Controlled experiments offer the advantage of objective variable control and reproducibility, though the findings can be difficult to apply to real-world materials due to their often highly artificial experimental design. Majority of the controlled flaking experiments to date have used glass as the flaking medium. Early studies employed glass prisms and plate glass, as these materials are relatively low cost and can be easily obtained. However, because of their angular form, the produced flakes do not resemble artifacts found archaeologically. Over the past decade, Dibble and colleagues introduced a more realistic glass core design that incorporated platform angle and dorsal convexity. As a result, their controlled flaking experiments produced realistic-looking flaking outcomes. Here's a short clip showing their experimental flaking setup.
Going.
While glass can be molded into realistic designs, shaping stone raw material into a uniform core design remains difficult. Existing studies shape stone blocks into standardized forms by using a saw and a sander. However, these core forms are again limited to simple angular geometries. As a consequence, it remains a major challenge to test results of controlled glass flaking on stone raw materials, especially if we are interested in incorporating more complex core shapes, such as in lavawa reduction. Here we take a quick look at the definition of lavawa reduction and see how a controlled flaking experiment can help expand our understanding of lavawa flaking. In his definition of preferential lavawa reduction, Eric Boyder outlined 6 defining criteria. The first 4 criteria relates to core morphology, namely the organization and shaping of the flaking surfaces. The last 2 criteria concern the application of force. In particular, the 5th criteria states that the angle of hammer impact needs to be perpendicular or 90 degrees to the striking platform. This direct percussion angle is said to be critical for the lavawa flake to detach parallel to the plane of intersection between the flaking surface on the top of the core and the preparation surface on the bottom. Doing so allows the fracture to travel through the prepared core surface and produce a large, broad flake. In other words, the angle of hammer impact or blow is a key to the predetermining flaking process of lavawa reduction. The importance of the angle of blow is supported by existing controlled flaking experiments. John Speth noted in 1975 that striking a core from an oblique angle causes the flake to be shorter and slightly thinner than those made from a more vertical direct angle of blow. More recently, Dibble and Rizek showed in their glass flaking experiment that increasing the angle of blow causes flake weight to decrease, such that a flake made on an oblique striking angle tends to be lighter than those made from a more direct hammer strike. In this study, we aim to test the relationship between the angle of blow and flake attributes among lavawa cores under a controlled flaking experiment. The first challenge in this study is to replicate identical lavawa cores. This is achieved by using an automated 3D milling machine. To make the core, we first modified a 3D model of an experimental lavawa core made by one of us and input the model into the 3D milling machine. We then prepared blocks of glass and chert to be put into the milling machine for shaping. The machine then uses a drill to mill the stone and glass block into a standardized Levallois core shape. Here are two examples of the milling machine shaping a glass and a chert block. This is an example of a finished glass Levallois core after milling. The core is spray painted for visualization purposes. The right figure shows the 3D digitized version of the core with the ridges highlighted. After the milling process, the shaped glass and chert cores are then subjected to control flaking. The mechanical flaking apparatus used here composes of a pneumatic cylinder with a hammer attachment. The core is secured in a mount positioned under the hammer. When the pneumatic cylinder extends, the hammer attachment extends down and strikes the core underneath. The vise under the core mount allows us to adjust the position and angle at which the hammer strikes the core. For the Levallois experiment, all cores were shaped to have an exterior platform angle of 75 degrees and were struck by using a steel hammer attachment with a beveled edge. We then varied two attributes during the experiment. The first is the location of hammer impact relative to the platform edge. This is called the platform depth. The second is the angle of blow. We vary between 0 degrees, which represents a direct impact, and 10 and 20 degrees for increased levels of tilt. Here's a video showing the flaking process on a glass core. Here are some examples of the flakes produced from the glass cores. While there is a great degree of regularity among the flakes due to the uniform core morphology, there is notable variation in the size and shape of the flakes depending on the platform depth and the angle of blow. In particular, when we compare the flakes made from different angles of hammer impact, the flakes appear to contract in its size and width as the angle of blow becomes more oblique. The effect of the angle of blow can be better visualized from these plots. Looking first at the left figure that plots different levels of platform depth by flake weight, we see that larger platforms lead to heavier flakes in general. However, with the same platform depth, flakes made by a direct vertical hammer strike tend to be heavier than those made from a more oblique strike. This difference in flake weight becomes greater as platform size increases. So what is driving this difference in flake weight? Looking at the figures on the right that plot the flake dimensional attributes, while there appears to be some difference in the length and width of the flakes made from different angles of blow, the main difference appears to be in thickness. Similar to the pattern in flake weight, we see here that flakes made from a more oblique strike tend to be thinner than those made from a vertical strike. To further explore this difference from the angle of blow, we superimpose the cross-section profile of the flakes to see how the fracture plane changes by different striking angles. Looking first at the left figure showing fracture planes of a vertical impact angle, here the fracture runs closely parallel to the plane of intersection of the Levallois core, resulting in long fracture trajectories. Looking now at the figures to the right that show more oblique striking angles, the fracture plane now is tilted more towards the core exterior surface. As a result, the fracture exits the core much earlier, producing flakes that are not only shorter but also thinner. So how do the chert flakes compare to the glass flakes? The two sets of flakes shown on the left represent chert and glass flakes made on a similar platform depth and the same angle of blow. It appears that the chert flakes are narrower than their glass flake counterparts. Looking now at the figures on the right, where glass flakes are plotted in red and chert flakes are plotted in green. It seems that the chert flakes tend to be shorter and narrower than the glass flakes, but not thinner. This suggests that there is some inter-raw material variability in the effect of angle of blow on flake attributes. However, the general effect of the angle of blow on flake size and shape is still apparent among the chert flakes despite the low sample size here. More samples are needed to allow statistical comparison. We can also look at the amount of force required to detach the flakes made from glass and chert. The figure here plots the relationship between flake weight and the percussion force as measured by the load cell output during the flaking process. Again, the red dots represent the glass flakes, while the green dots represent the chert flakes. It is clear here that for a flake of a given size, it takes substantially more percussion force to detach a chert flake than a glass flake. This finding is of course expected and not that surprising, given the difference in raw material property between glass and chert. The findings so far indicate that the angle of blow has an impact on the size and shape of flakes. A more oblique strike causes the flake to be lighter and thinner. This is because a greater striking angle causes the fracture plane to tilt more towards the core exterior surface, making the fracture exit the core much earlier. This finding supports Boyder's Levallois criterion that a direct hammer impact angle is critical for the fracture to run parallel to the plane of intersection among Levallois cores, allowing the production of a large Levallois flake. The effect from the angle of blow is apparent in both the glass and chert flakes produced here, though the chert flakes do seem to be shorter and narrower than the glass flakes. This difference indicates some inter-raw material variability in the effect of the angle of blow. A major implication of this study is that the angle of hammer impact can cause considerable variation in flake size and shape. However, because the angle of blow cannot be directly observed from the flakes, it remains an archaeologically invisible factor. Being able to identify this major source of lithic variation represents a major challenge in future stone tool experiment. In conclusion, we demonstrate that a controlled flaking approach to lithic experimentation is useful to objectively test the influence of knapping parameters on flaking outcome. The nature of the controlled setting allows researchers to quantify these relationships and further develop general models of flake formation. In this respect, the incorporation of the 3D milling machine represents a major advancement, as it allows for the production of multiple test cores with complex surface geometries from varying raw material types. This opens up a new range of possibilities for researchers to test models of flake formation on real-world archaeological forms. Returning to the Levallois flake formation experiment, our future research aims to increase the sample size in order to perform meaningful statistical comparisons, as well as conduct geometric morphometric analysis to analyze flake shape variation beyond linear dimensional measurements. Finally, we also plan to further investigate the effect of core surface convexity and hammer material on Levallois flake formation. Thank you for listening, and we hope you enjoyed hearing about our research. Please check out our website and follow us on Twitter for updates on our research here at the University of Wollongong in Australia. Scan the QR code on the right side of the screen to see and interact with a 3D model of one of our Levallois cores. Thank you.